Now, we've done an experiment. We have a tube here. We have a little hole in the bottom of the tube. Not sure how visible that is. There's a little tube in there. It's got an 1/8 inch inner diameter. So if I put water in it, fill it up with water, and maybe with my finger over the hole, and then take my finger off the hole, water's going to spray out. Okay. If water's at a lower level, it's going to spray out, but it's not going to travel as far before it hits the ground. Okay, so water is going faster when it's deep. The water comes out faster when there's more water above it. It comes out more slowly when there's less water. By energy conservation, we expect the kinetic energy of the exiting water to be proportional to the pressure, water pressure. Okay. The velocity of the exit, since kinetic energy is 1/2 mv squared, v is proportional to the square root of kinetic energy, which makes it proportional to the square root of the pressure. The rate of change of depth is what we call, the rate of change of depth in the cylinder is proportional to the velocity of the exiting water. Exiting water is moving faster, water's decreasing up here faster, because why? Well, among other things, you're losing potential energy up here relative to this point, and thereby gaining kinetic energy down here. Now, there's also some loss due to dissipation, friction around the boundary of that hole. And that's one of the things we want to kind of make a determination of with the experiment. Right now, we're just trying to see what kind of depth function we might have. Depth is a function of time and so forth. And actually, we kind of know because we've done some observations, and we've found that depth versus time appears to be extremely well fit by a second order polynomial, a quadratic function of time. The depth appears to be a quadratic function of time. Why should that be? Okay, well, that's what we're looking at here. So the rate of change of the depth in any case is proportional to the speed of the exiting water. Make sure we understand that. Now, pressure is proportional to depth. If you got twice as much depth, then you have to support twice as much water, but with the same cross-sectional area down here. And that makes the pressure twice as great as it would be if depth of water was half as great. Okay, so pressure is proportional to depth. We established that a little more in a little more detail elsewhere. But that's one thing we're going to use here. Now, if we let y stand for the depth, then velocity of exit is proportional. Actually, it's equal to dy dt. That should be obvious. And that then in turn is proportional to the square root of the pressure, but the pressure is proportional to depth, which is y. So that's proportional to y. The rate of change of y is proportional to the square root of y. Now, we can write that as a differential equation. dy dt is some proportionality constant multiplied by the square root of y. We often use k for proportionality constant. And note that this is not the k exit. The big capital K exit is kinetic energy of the exiting water. This is a lowercase k, if you want to think of it, but it doesn't have the exit subscript on it. So it's a different constant. It's not an arbitrary constant. And actually, well, it's involved with the ratio of the area of the hole to the cross-sectional area of the cylinder in a way that I'll elucidate with in writing. So we don't want to get into that much detail, just get the conceptual idea of why this thing of why the depth versus time is a quadratic function. Okay, so how do we solve this? Well, everybody in the class has had differential equations. You don't even need differential equations. First semester calculus, you usually solve a problem like this. You're just going to put the dy over the square root of y and the dt over here with the k, and then integrate. Okay, that's called a separable equation, and my differential equation students recognize it after thinking about it for a minute. Just a plug, you really ought to think every once in a while about how you classify different differential equations so that when you see one, you'll know what type you have, and that will hopefully invoke the method of solution. And that's not confined just to the end of by the end of the differential equation class. You know, you need to continue to understand differential equations if you're in a rigorous STEM field. Okay, so anyhow, we have this integral. It's a simple integral. You get 2 square root of y equals kt plus c. C being an arbitrary integration constant. Well, it means y is square of kt plus c. Where I've ignored the 2, I let the k and the c, which are unspecified constants, I let those constants absorb the 2. And really, I shouldn't have done that because the k is going to be pretty specific. So I'm going to rewrite this real quickly. We're going to let the c absorb the 2. We don't need too many 2's running around. It's a 1/2, not a 2. So we get y equals 1/2 kt plus c, where k is whatever the proportionality constant is here. Again, I say that depends on the relationship between pressure and depth, and also on the ratio of the hole here to the cross-sectional area, and ultimately has to take into account, if you want it to be accurate, this is the ideal case. In the ideal case, k would be related to that ratio, et cetera. In the real case, we find that we deviate from that somewhat because of dissipative energy losses. Okay, well, there we have it. And this is why our depth y versus t is part of a parabola. Of course, the part that corresponds to the reality of the experiment ceases when you reach the lowest depth, okay? In other words, when you reach the depth of the hole. So, you know, this line here would be y equals the hole position. Not leaving myself enough room here. And you don't really know that. And the reason I mention this is if you have your data and get decent data, even half decent data, your data points will be very well fit by a quadratic function, and you can plug into Excel and add a degree 2 polynomial trend line and actually get your function. Okay. So this is why that worked.